So this series of videos is going to be about the structure of other solids other than the metals that we've been talking about. So we're going to look at alloys, crystalline nonmetals, and ceramics. So first, the alloys. So what is an alloy? Well, an alloy is simply a metal that you've taken and you've added a bit of some other element or elements. When you do that, you change the properties of the host metal. Alloys, in fact, have a long history in human civilization. We knew about metallurgy and its techniques long before we had even discovered the word chemistry. A somewhat related term that might be confused is ore. An ore is just a naturally occurring mineral that's a mixture of compounds, or perhaps a single compound, from which elements like aluminum or copper or iron could be extracted. There are two classes of alloys that depend sort of on how the atoms that make them up are arranged. First, there are homogeneous alloys, where the host metal and the guest metal, the bit that you've added in, is uniformly distributed, spread out. Then there are the heterogeneous alloys, where the guest atoms, the element that you add in, tends to clump together in small islands. Here's a picture that shows that. So the first image on the left is more or less a homogeneous alloy. You see that the red atoms and yellow atoms are pretty much evenly spread out, although there is some grouping of the reds and the yellows together. This is more clearly a heterogeneous alloy. So you see all the yellow atoms in the middle are clumped together, and the red atoms form a shell on the outside of this core shell structure. Here we see, in the last picture, the yellow atoms and the red atoms clearly clumped together in larger groups, what we call a cluster in cluster. There's another way of talking about alloys that's based on their structure. So we need to know where in the crystal lattice of the metal are you going to put these guest atoms, these little extra elements that you're adding in. And there are two ways of doing that. The first way is called a substitutional alloy, where the added element substitutes for one of the host metal atoms. In other words, you just pluck out a host metal atom of the lattice and you're going to stick in a guest element. But this guest element has to be about the right size, just right. It must be about the same size as the metal, the host metal itself, by plus or minus 15%. Otherwise, it won't fit. It'll be too small or too large. A great example of a substitutional alloy is bronze. You might have heard about the Bronze Age of human civilization, so a very important metal in our history. So this is a substitutional homogeneous alloy. So here you see the brown copper atoms, and we've added into that some tin, represented here by the silver. So you'll notice what we've done is plucked out perhaps a brown atom that should have been here and replaced it by one of these silver tin atoms. Here's a little bit of the crystal lattice that might be made by plucking out some of the copper atoms and replacing them with tin. So there's a possible unit cell for bronze. So how does this change the properties? Well, you might recall when we talked about metallic bonding that there's this electron C model. And it turns out that the little islands of positive charge surrounded by the electron C are able to move a little bit relative to each other. So you can imagine we have planes of atoms that are able to slide past each other in this sea of electrons. But when you throw a zinc atom in, it actually disrupts the lattice structure enough that effectively they're like bumps in the lattice now. And these planes of atoms can no longer slide on top of each other as easily. So it creates kind of like a friction almost. It's kind of a crude argument, but it works. The effect is that it makes bronze harder and stronger than pure copper, which was great for Bronze Age civilizations because then you could make stronger spears and shields and swords, and well, I guess that was a good thing back then. So there are other substitutional alloys that you may have heard about. Brass, which is copper and zinc, or pewter, which is tin and copper, and the most important ones, stainless steel, and a lot of other iron-based alloys. So here the host metal is iron. Stainless steel, in fact, is made up of nickel and chromium. So you see it says here about 10% and up to 20%. So this highlights for us that alloys are really mixtures. Mixtures, right, are variable. They don't have to have a definite composition. So you can add a little bit more or a little bit less, up to a point, generally. The other type of structural alloy, a place where we can put these guest elements that we're adding, is an interstitial alloy. So you'll remember an interstice, or an interstitial space, is the little hole that's formed when we stack atoms on top of each other. So here's an example of some atoms that we've stacked together in a close packed arrangement. So we've made a layer of red atoms. We stacked on top of that a layer of purple atoms. Notice that the purple atoms rest in the little divots of the red atoms. So we're going to consider these 6 atoms, these 3 red atoms here, and these 3 purple atoms here. Chop them out so that they are right here. So you'll notice that there's a little hole, a little interstice here. So if we tilt this on its side, we can get an idea of the shape, kind of this hole. So it's surrounded by 6 atoms. 1 on the top, 1 on the bottom, and 4 on the sides. So right here you can see a 4-sided pyramid. So this purple atom is the pinnacle of the pyramid, and these 4 atoms right here, 2 purples and 2 reds, make the sides of this 4-sided pyramid. We've got another pyramid then resting on the bottom, so this red atom is the pinnacle of the pyramid that's pointing down. So that shape with these little triangle faces makes a shape that we call an octahedron. So this hole is an octahedral hole, and if you have an atom that's small enough, it can fit inside this hole. There's also another kind of hole in this lattice, so formed by these 3 red atoms and this purple atom, and you can kind of see in the shadows here that there's this little empty divot. You can kind of see through the purple atom there. So if we pull that out right here and tilt it on its side, you see that we have another kind of shape, a 4-sided shape that we call a tetrahedron. So the little empty space that we see right there is called a tetrahedral hole, and you need an even smaller atom to fit inside a tetrahedral hole. So let's look at an example of an interstitial alloy. This alloy is carbon steel. So here's an example of an iron crystal lattice, a face-centered cubic lattice called austenite, and iron forms this at high temperatures. So if we sprinkle in some carbon, the carbon atoms can fit inside the octahedral holes inside this iron. So how likely is it that any given element that you add to a metal will be able to fit into one of those holes? Well, it really depends on the relative sizes of the atoms, and this table helps us figure that out. So what we're going to want to calculate is the ratio of the radius of the non-host atom, that's the element that you add in, to the radius of the host atom. So for example, if we're looking at steel, where we've got carbon added to iron, the radius of a carbon atom, 77 picometers, radius of iron, 126, and we calculate a ratio here of 0.61. That places it in this range. There's a little note here that reminds us these ranges are kind of crude, so you should take this with a grain of salt. But this says that the carbon atom would be about the right size to fit in the octahedral hole if you have this kind of lattice, either a hexagonal closest packed lattice or a cubic closest packed lattice. You'll recall that face-centered cubic, which was the austenite lattice that we just looked at, is a type of cubic close packed structure. So here's some of the properties of carbon steel. So the properties depend on how much carbon we add. Now in actuality, the situation is a little bit more complicated than the austenite that we just looked at, because as the steel begins to cool, it turns out it converts from face-centered cubic to body-centered cubic. We get a ferrite structure, and the carbon atoms with a couple of iron atoms precipitate into these clusters, Fe3C clusters. Now these clusters combine to disrupt the lattice structure, and just like we saw in the case of bronze, reduce the slippage of those metal planes, and that increases the strength of the metal. So steel is much stronger than iron because of these clusters being around. How strong depends on how much carbon we add. So for example, high carbon steel is quite hard, but the downside is that it's brittle. So it's good for making cutting tools, but not so good for making cables and things that need to have a lot of tensile strength, because you don't want your cable to be brittle on your elevator. Bad news. So in the next videos, we will look at some of the properties of crystalline solids of nonmetals.